Okay, all right, so let's get started. Welcome everybody to our seminar series on trustworthy data science and AI. We are resuming this this seminar series in this fall. And today we're super excited to have Dr. Wang-Chiew from Meta AI to talk to us about deep data integration. Wang-Chiew is a research scientist manager at Meta AI, or previously Facebook AI. So she was, before that, she was also the head of Megagon Labs, where she led research on building advanced technologies about search experience, and which included, for example, one of the topics today, data integration, and also information extraction, text mining, and summarization. Before that, she was also a professor of computer science and at UC Santa Cruz. She also, I think, had time with IBM research at Amazon. So without further ado, Wang-Chiew, the floor is yours.
Thank you, Tianzhen. Yeah, so good afternoon, wherever you are. Good morning, everyone. Thanks for taking time to attend this talk today. I understand it's also a holiday there, so I double appreciate it. I'll be talking about deep data integration and specifically on the topic of how deep learning techniques have been applied to data integration problems in the recent year. Now, this talk is largely based on my Sigma talk last year, so I apologize if you have already heard a version of this talk. It'll be quite similar, all right? So, oops. Okay, yeah, can you see it? Yeah, okay. So first of all, this is, I believe, a database group. By the way, feel free to interrupt and ask questions. I find that is usually more constructive as for the talks. If you just, feel free to ask questions. So first, I imagine most of you know what data integration is, so I'm going to just, zoom through this part. All right. The goal of data integration is to really provide uniform access to different data sources. That is, if data integration is done correctly, right, the user gets the illusion that she's only accessing one data source, not, 5 or 6 data sources underneath the hood, right? So So in particular, all these different data sources, they may be in different format. They may use vocabulary that look the same but mean different things, or look different but mean the same thing. They may be in different structure, as I mentioned, and they also may be dirty, right? Some values may be missing, some typos, this and that. So you want to be able to provide the user still with the illusion that she's accessing one data source in the context of all this heterogeneity going on. So that's a difficult problem, right? Traditionally, there are 2 approaches to data integration. The first one is called virtual data integration, sometimes also known as data federation. The second one is the data warehouse approach, where I think probably most of you heard about this. I'll go through in a bit more details. And today, I think the latest term for integrated data is really data lakes. Okay, so what is virtual data integration? This is the diagram here that shows how virtual data integration looks like. There's a number of data sources, right, which may be heterogeneous, as I mentioned before. And then there is a global schema here, which is to the user what she sees of all these data sources. So just one uniform way of representing all these data sources. When the user poses a query against the global schema, the data integration system will have to do a lot of work to translate or rewrite these queries to maybe different queries against all these different sources, and then get the results back, massage them, manipulate them into a format that you can return to the user. Okay, so there's a lot of work here to answer user queries. So no data actually exists under the global schema, but it appears to the user that there is data sitting here under the global schema, and that's how she's querying it. Okay, so the data warehouse approach has a very similar diagram to virtual data integration, except that now there's actually data materialized under the global schema. So that's the only difference. There's actually data physically migrated to conform to this global schema sitting underneath the hood. And then when the user queries this, makes a query against this global schema, the query can be immediately executed in the data warehouse and returned to the user. So a lot of work in the data warehouse approach is how to migrate all this data sitting in different formats with all these heterogeneity issues involved into this global schema, right? So it's a lot of pre-computed work so that it becomes easier to answer user queries. All right. So the third approach is the data lake, right? Data lake, in my opinion, is in a league of its own. A data lake is simply a collection of, usually a massive collection of raw data sources, right? It can be CSV files, JSON files, again, in different formats, very heterogeneous. Just like in virtual data integration and data warehouse, one of the main challenges here is how do we allow the user to query all this data sitting like just out there, okay? To do this, we need to understand how to do data discovery, extraction, cleaning, integration dynamically, right, on demand over the data lake. And how to do this at scale, because we are usually talking about a lot of data in a data lake. So all the problems that exist, a lot of these problems that exist for data lake also exist in virtual data integration and data warehouses. The pictures that I showed you earlier, as I was trying to explain, don't tell the whole story. In the former two cases, virtual and data integration and data lake, a lot of work has been put into data discovery, extraction, cleaning, right, and rewriting of queries to answer queries. So whether it's virtual data integration, data warehouse, data lakes, to bring all these relevant data sources together to a state where the user can pose queries, typically involves many steps, right? First, I mean, how do we identify all these, what are the relevant data sources that can be used to answer your query? And keep in mind that all these sources, again, they may be of different formats. Some are unstructured, some are structured. They can be also of different modalities, right? Some are in text, some are in videos these days, or images. So how do we identify, once we identify the relevant data sources, how do we extract the relevant information from these data sources, right? How do we understand how these different data sources relate to each other, so that this will help you, help you in the process of bringing the data together to return to the user, or bringing the data together under the data warehouse, all right? So very often we also have to understand how to deduplicate all some of the data that exist, partially duplicated across this different data sources. So deduplication is also an important topic. And as I've mentioned a couple of times by now, we also have to deal with missing values, dirty data, or wrong data even, right, in these data sources. So data integration ecosystem encompasses all these different tasks, and is also sometimes called the data preparation and data integration process. But each of these steps are important in the data integration ecosystem, right? So what I've done is just to give you a very quick overview of the data integration ecosystem. In this talk, I will focus primarily on one aspect of the ecosystem, which is the entity matching part. And to do that, I will first give you a very quick overview of deep learning, just enough to get us to do a deeper dive into entity matching with deep learning models. In this deeper dive with the entity matching as a use case, my goal is to show how specific deep learning models, in this case, transformer-based pre-trained language models, can be easily applied actually to entity matching. After I discuss entity matching with you, I'd like to take a step back and discuss why deep learning techniques have been so successful on not just entity matching, but also other data integration problems. and what I also believe are some of the interesting challenges and opportunities for the data management community. Okay, so I think probably most of you know what the neural network is. This is very quickly deep learning algorithms are really a type of machine learning algorithms, right? Based on neural networks. You probably have seen a diagram like this before. It has an input layer of neurons on the left, and two or more hidden layers. Usually deep learning networks have lots of hidden layers, right? And one output layer. Deep learning techniques simply refers to neural networks with several hidden layers here, and hence the name deep, right? As you know, deep neural networks are meant to mimic the way the human brain functions, and that's where the neurons are connected together in complex ways. So just zoom in on one neuron here, right? On the left, we have the inputs coming into the neuron. And here we have an activation function, right? In standard logic circuits, the activation function is a step function that will result in the value 0 or 1. In the case of general neural networks, they are typically nonlinear functions, which take as input a weighted sum of inputs here, right? Together with a bias. So it's a function of a weighted sum of the inputs with the bias B, right? W's and B's. Nonlinear functions tend to make them more sophisticated and more expressive in general. Information that is passed between network layers through this activation function, and the W's and B's get adjusted every time in every step of the learning or training process, if you like. So what happens during the training time or the learning time is that the network backtracks to try to minimize a certain loss function, in a process adjust the W's and B's so that in the end, right, these W's and B's get adjusted so that the model learns what are the quote and unquote right values of W's and B's to approximate the relation between the input and corresponding expected output based on the training data, right? So yeah, there's a lot going on, but this is at a very high level, what is going on in a neural network. So it's a process during training, it's a process of adjusting the W's and B's so that you end up having a good approximation function of the input and output training data. So now with this in mind, you can imagine that there are lots of different neural networks out there. I believe this website is already outdated. And this website is called the Network Zoo website. It curates and explains the different neural networks out there. I'm not going into details. I just want to show you this page because it looks nice, and it just gives you the visually that there are lots of neural networks out there. Okay. I think what is important is that to know there has been a lot of neural networks development out there. And one of the more groundbreaking paper is this paper in NeurIPS 2017, titled "Attention is All You Need," that is built on top of all these different neural networks that were shown, some of these neural networks that were shown in the previous slide. As you can see, this is a transformer-based architecture that they were proposing at that time, and is sitting on top of all this different neural network architecture. Just very quickly, this paper, at a high level, this paper describes the following architecture for transformers, which has the following useful properties, right? Which is why it's getting it is being used widely these days. So first, it's a self-attention mechanism, which is also the title of the paper, in that it's able to relate a word, right, an English word, to its neighboring words, whether the words are on the left or on the right. Okay. In other words, it's able to too many words, to put in another way, right? So it is able to contextualize the meaning of a word based on its context. This was kind of groundbreaking at the time because previously all the word models were isolated on single words. So if you look at these two sentences, the river bank was covered with flowers. The bank issued a financial statement. To us, it's very obvious that these two words bank, they are different. They mean different things in these two different sentences. In previous word models like word to bag or glove, the embedding of bank will be the same, whether in this sentence or in this sentence. Now with transformer-based models, the word bank is contextualized, so the embedding is dependent on the sentence it occurs with, right? So yeah, this gives it a very powerful twist, because now language models are able to distinguish what the bank means here versus what the word bank means here, right? So the second property that it has is multi-head attention, which means it can relate a word not just to its neighboring words. It can relate a word to its neighboring words based on different relations. So different semantics. For example, it may be subject-verb relation, subject-adjective relation, pronoun-noun, all these different kind of language model relations. So it's able to get all this underlying semantics because of its multi-head attention capability. So it is, to put it simply, perhaps is able to take different views just by looking at a sentence of the relationship between words. So it has a deeper understanding of sentences, in other words, okay? So the third property, very useful property it has, is the positional embeddings, right? Self-attention itself is very permutation invariant. But as we know, sentences, the order of tokens, order of words, they are very important. So the paper proposes actually a method to encode the positions of the tokens so that the language models, the transformer model, is able to understand this word occurs before that word. Yeah, so there are many other tricks mentioned in the paper, but I think these are just the main ones. So this is the architecture that was laid out in a subsequent paper, BERT, which I'm sure many of you have heard of. BERT is one of the most popular pre-trained language models out there that has been widely deployed in many applications. So BERT is actually based on a popular transformer-based model that was published in 2017. Now, BERT uses bidirectional layers of transformers. So it takes this transformer as a building block. Now it makes it, several layers of it and interconnects them, as the architecture here shows, right? The blue ones are the transformer models. Each transformer feed forwards to every other transformer in the next layer. And then in the final layer, we obtain the output, right? Tokens. So, excuse me. For example, the base model of BERT has 12 such layers, and larger models of BERT has more layers, like 64, 128 layers. And today, models are getting bigger and bigger. You can imagine there are more and more layers in here with even more and more parameters. So BERT became very popular, at least at the time, because not just because it's powerful, but it also offers a fine-tuning paradigm for many different types of natural language processing tasks, right? You must understand a little bit of context here, because before that, there were already language models that were powerful. But then to use the language model for different downstream NLP tasks, you have to spend a lot of time re-architecting the model to fit your application. But BERT offers a very easy way to fine-tune the same model, right? The same architecture, but just fine-tune it so that it suddenly is magic. It works for different NLP tasks. And I'll talk about fine-tuning a little bit later. And that's how we use it for entity matching. Okay. So BERT is one of the earlier transformer-based pre-trained language models. As I mentioned, there were earlier models, but one of the greatest thing about BERT is the ability to reuse the model through fine-tuning. When it first came out in 2019, it was already beating the state-of-the-art techniques in several of the NLP benchmarks. And then ever since, a lot of transformer-based pre-trained language models were developed. Most of them were developed with specific goals in mind, right? For example, the GPT family is developed to target sequence generation, while things like Albert or Distilbert were developed with smaller memory footprints in mind to allow for easier deployment, right? Yeah, so let's talk about, I'll talk about fine-tuning in a bit to show you how easy it is to fine-tune these pre-trained language models for entity matching. So, but before that, let me just go through the entity matching problem, which is one of the more prevalent data integration problems in data integration system. This problem has been around for a long time. And what is this problem? Is given two data sources to find all pairs of entities, one from each data source, that refer to the same thing, okay, same real world entity. In other words, we would like to output all pairs of entries, one from each source, that refer to the same real world entity. Maybe it's the same product, same person, same company. So you just want to find which pairs are referring to the same product, same person, or same company. This sounds like a really simple problem, right? Except that if you have 1 million records in one data source, another million in another data source, and keep in mind, 1 million is not a lot these days, right? You end up with 1 trillion record pairs to compare. We don't want to do 1 trillion pairs of record to compare, right? So I'll come back to this point in a bit. And also for each pair, candidate pairs, you have to apply some intelligence to understand how to judge whether two pairs are really the same thing or not, which can be really tricky. Now, entity matching is not a new problem. In fact, it's a really old problem. Chances that if you need to deduplicate data, work on knowledge-based construction, you will come across entity matching at some point. This entity matching goes as far back as in 1969. That's like more than 15 years ago. The paper by Feligi and Santer on a theory for record linkage. And since then, it has lots of paper on entity matching. These are the more recent ones. And you may have also heard of variations of this name, like entity resolution, record linkage, reference reconciliation, duplicate detection. They all mean the same thing, right? So Gurujada et al. Actually made the joke maybe that the entity matching name itself needs, reference reconciliation. Okay, so my next few slides will be largely based on this paper, DITO, Deep Entity Matching with Pre-trained Language Models. This is work I've done with Yuliang Li, Jinfeng Li, Yoshihiko Suhara, and Anhai Don, published in last year VLDB. So again, the goal is to take two collections of data. So DITO does not have the restriction that these two collections of data must be relation tables. One can be a table, one can be a JSON file, for example. It doesn't matter. But the goal is, again, to output all pairs of entries that refer to the same entity. Now, the example here, I show you two tables, table A and table B, with 3 records each. But you see that in table A, there are 3 columns. In table B, there are only 2 columns, right? So, the goal is to output all pairs of entries that refer to the same product in this case. To solve the entity matching problem, as I mentioned before, is well, I didn't mention before, sorry. The work is typically divided into 2 phases. So the first phase is called the blocking phase. The goal of the blocking phase is to reduce the number of pairwise comparison for the next phase, the matching phase, which does the work of actually determining which pairs of entities are the same thing. Okay, so recall that earlier I mentioned if you have 1 million tuples in one table, 1 million tuples in another table, you end up with 1 trillion pairs to compare. So that's what the blocking phase is for. Instead of dealing with 1 trillion, it usually applies some heuristics, right, to reduce 1 trillion to maybe 100,000. Okay, the heuristics are usually very simple heuristics with high recall, so that but it has low precision. Okay, it's just the goal here is to do it fast to reduce things that you clearly know should not match, so you don't spend time looking at them. Okay, so that's the goal of blocking, so that the matching phase can then come in and look at the remaining candidate pairs to see, to study more closely whether each candidate pair is a real match or not. Okay, so if you look at the example I've shown you earlier with 3 pairs of records in each table, if you do a Cartesian product, we have 9 pairs of tuples to compare, right? It can apply a simple heuristic such as the candidate pairs must share at least 1 token in the title column, right? If you apply that heuristic, suddenly you only have 3 pairs to compare, right? And these 3 pairs are shown by the dotted lines here. So from 9 pairs, you reduce down to 3 pairs immediately, okay? Then the matching phase comes in and look at these 3 pairs to study which of these 3 pairs are matching pairs, okay? So out of the 3 candidate pairs, only the first and the last one are matching pairs. The second one is actually not a matching pair. So at that time when we were doing this study, in as early as in April 2020, the state-of-the-art entity matching solutions failed to get any of these correct. Okay, for all these 3 examples, it was giving the wrong answer. So as we were digging in, studying these examples, we realized a couple of things. There are a couple of observations here. First, language plays a crucial role, right, in helping us determine whether a pair of entities should match or not, right? This is especially so for text-heavy data, right? Like this case, the title column has a good number of words in them. So when you have text-heavy data, that's when language models comes in very useful. The second observation is knowing what to pay attention to when making these matching decisions is very important also. And knowing what to pay attention to usually changes from pair to pair, right? There's no fixed rule. So to know that the second pair is not a match, right? We need to know that the addition of the software is very important here, right? To determine the unmatched decision, right? Even though the titles look very similar, the version here is is very important. For the last pair, for example, to know that these 2 pairs are matching pairs, right? Even though their title column looks very different, right? You need to know that the model number plays a crucial role here. So in one case, the model number is sitting nicely in a separate column under this second column here. In this case, it's embedded in the title, right? And looking maybe slightly different. So this also brings to us to the last point that it's also important to be able to deal with dirty data. Sometimes you have model numbers not occurring in the same place, right? And maybe looking slightly different. You still have to be able to make that out, that these are model numbers, and they are very important for the matching decision here. So, so with these observations in mind, we thought, okay, pre-trained language models could help here. And that's where we started to look at how to use pre-trained language models for entity matching. So Ditto fine-tunes pre-trained language models to do entity matching. And recall that pre-trained language models are already trained on large data sets. Like, for example, the BERT model is trained on 2 large corpus, the book corpus and the English Wikipedia. And they, without fine-tuning, were already giving us really strong baselines for a lot of NLP tasks at that time. But since the architecture of BERT makes it very easy to tune the model to be specific for the task, we tried that as well, right? And so maybe before I show you the results, let's talk a little bit about how we fine-tune pre-trained language models. Okay. So what does fine-tuning means? Fine-tuning means you remember that there are layers in the pre-trained language models, lots of layers of transformers. Fine-tuning means freezing some of the layers, maybe adding a couple more layers so that you can adjust the weights and biases, if you remember all these parameters in there, right, of some of these layers, okay? A typical approach is actually to freeze all the layers of the pre-trained language model and attach some new layers on top, and then you just tune the new layers, right? So for example, in Dito's architecture is here, we attach a linear layer. Where's my cursor? Okay. The linear layer here on top of this boxed is the pre-trained language model, right? It's a black box to us, right? So it could be any pre-trained language model like BERT, DistilBERT, Roberta. Okay, you attach a layer on top, and this is usually called the task-specific layer. We fine-tune the model using training data specific for entity matching. In this case, a couple of hundreds of pairs of training data telling us this one should match, this one should not match. Okay, so to train the model for Dito at least, we need to pass our training data through these language models, right, as follows. Oops. So just to go back to this diagram a bit. So remember we need to pass in pairs of records so that the model can tell us whether they're match or not match. Okay, so these records are two sequences of tokens, and so we need to serialize them so that the language model knows that these are records in some ways. So the first thing to do is to serialize each entity. So the way we do it is just, you know, like the first record with attribute title, you put a column token, and then you put a value token before you put the description of the title. You put another column token for the second attribute, and then a value now, and then column price value. So you just serialize the record in this way. So we have two records. The way you pass it to BERT is to put a special token CLS, serialize according to what is shown above here, put a separator token, and then serialize again for the second record, and then put a separator token, and then pass it to BERT. Okay, so this is how at the bottom it looks like. You pass these two records to BERT, it goes through all the layers, and then it outputs the linear layer looks at the first token. I'll explain this in a while. Goes through a softmax function to turn it into 0 or 1 to tell us whether it's match or not match. So the CLS token here, right, here, which may be a bit small to see, but it's a CLS token, is one token that summarizes all the contextual information of the entire record, right? So that's why looking at just this token is kind of enough. Even though nothing stops you from looking at more tokens, but looking at this token is usually enough. So, so by passing your training data through examples of match or not match through this BERT model, the weights get adjusted, right, to be a better model for entity matching in this case. All right. So as I've mentioned before, this boxed thing here, we're not limited to BERT. You can pass in other pre-trained language models like DistilBERT, Roberta. We actually use Roberta for better performance in our experiments. And DistilBERT is a smaller model. It actually is faster to train and faster in spitting out the prediction as well. Okay, so that's it for fine-tuning. So in Dito, we actually fine-tune, I think, all layers, right? Just let it go ahead and adjust the weights and biases of all layers. but you can choose to freeze some of the layers and just tune the linear layer, right? But that's all fine-tuning means. So it's the same architecture, and that's why it's getting so popular these days. It's very easy to fine-tune for your different applications. So we don't just do that actually for Ditto. We also do a couple of other things to help it perform better. So 3 things we do. The first is what we call injecting domain knowledge, and which is to allow users to specify which type of information is more important. So this is to help the language model, know what to focus on, right? Because if you have a long sequence of tokens, sometimes it's not clear, what to pay attention to, right? So if we have domain knowledge, like model number is important, right? So that's what we do for the product case. We insert some tags along the model numbers, right? It's an open ID tag and a closed ID tag. So just by inserting a tag, you give it it's like highlighting the text, you tell the model, maybe take a look at this closer. Okay. So we do this for later when I show you the experimental results, we do this for different domains. Like for example, for products, you can highlight product IDs, the brand configurations. For employers, you can highlight, employers, you can highlight the people, or you can highlight the 4-digit phone number or the street name of the address, right? For publications, you can highlight, which are names and the year and the publisher, right? So it's just a matter of highlighting. We use, how do we highlight? We just simply use a spacey or regular expression here to grab out the sequence of token and then insert the text, okay? Another thing we do is span normalization, right? Span normalization here means, sometimes people write their phone numbers in different formats. We just change all the phone numbers to the same format so that it becomes easier for the language model to realize that, well, this is a phone number, okay? So it's just a normalization of the formatting thing for easy things like phone numbers, maybe addresses, zip codes, right? So it becomes easier for the language model to know, well, this is a phone number, this is a zip code, okay? So which one is the same? It's easier to know. The second optimization we do actually is summarization. And this is to me an important one, because pre-trained language models have a hard limit on the sequence they can input. If you look at the diagram again at the bottom, is the fixed size number of tokens on what you can pass in to the language models, right? So now if you have, maybe for most cases, the 2 records will have a fixed size too. But if you have text in your data, right, sometimes one column can be so long, right? So chances are you will exceed the hard limit of these language models. So we need to do something about that, because otherwise, to pass in 2 records, the records get truncated. You're not doing a fair comparison. So you miss out a lot there. So what we do is to keep only the essential information using a very simple technique in the implementation. In this case, keeping only those tokens with high TF-IDF. But you can imagine using other summarization techniques, like, if you have a long text summarized into 2 sentences instead of like 10 sentences, right? So the third optimization we do in Ditto is data augmentation. This is done to reduce the amount of training data required. And we apply different operators to create more training data. For example, one very simple operator in the relational case is to swap the 2 records, right? Or swap the order of the attribute value pairs. Why is this important? By swapping the records or the order attribute value pairs, suddenly you have more training data. And you're also telling the model to learn harder, right? That these 2 records match. It doesn't matter whether it's this first, that first, or, the second one first, this first, right? These 2 records match. It doesn't matter if I tell you price column first, then the title column later, or the title column first and the price column later, right? They should match no matter what. So you're forcing the model, in this case, to learn harder in some ways. What is the thing that really matters in trying to come up with the match or non-match decision? It's not the order of the records. It's not the order of the attributes, right? So these are the things we do. Data augmentation. DITO uses a technique called mixed DA, which is more complex than what I've just told you about, swapping the order of the records or swapping attributes. In this case, I won't go into the details, but the observation is that sometimes data augmentation operators, such as those that, for example, drop a span of text, can actually change the whole result of entity matching. So mixed DA actually interpolates the result so that the original text and the augmented text are closer together, right? And not too far from, so there'll be less distortion, in other words. Separate paper on that, and I wouldn't talk about this, except to say that, yeah, it's just to smooth out the distortion. So we experimented DITO on the following benchmarks: the Magellan, Magellan benchmark, the WDC product matching data set, and also an internal data set at a time at Megagon Labs. So Magellan has 3 domains: publications, products, and businesses, and structured into 3 categories: structured, dirty, textual. Structured simply means there are tables. Dirty means there are some values missing, and textual means the data has a lot of text in it. The WDC product matching data set is much larger than Magellan. It's more than 200 product pairs to match, and it has 4 product categories shown here, divided into 4 sizes: small, medium, large, extra large. Okay. Yeah, so what we did was to run a deep matcher, which was the state of the art at that time, and then also DITO to compare the results. We compare the F1 score and the training time, but the training time is not shown here. So this is one, this is one experiment result with the Magellan data set. As I said, we ran with Roberta to get better performance. It's a huge table, but I think here's what you need to focus on. So DITO, first thing is that DITO consistently outperforms deep matcher on all data sets in the Magellan benchmark. And particularly, if you look at the yellow row here, is doing well also on small data sets where the available training data is small. Okay, so when you have a small size, we split it into training, validation, tests. Okay, so just imagine like maybe 200 label examples here, something like 200-300. So DITO also outperforms deep matcher when the data set is not only small, look at this row here, but also noisy or text heavy, right? So this is dirty, this is the noisy data, and the text heavy one is, which one is the text heavy one? I think it's also the Walnut Amazon is the text heavy data. Okay. Sorry, the textual is a text heavy bit of data, not highlighted here. That's the textual case. So yeah, so the yellow ones, the orange ones show that they're more robust when they are not only when they can be dirty, right? So these are like dirty data here. So here's the result for the WDC product data sets ran with distilled birds. In this case, this is a smaller bird model, which has faster training time. I think the main observation here is that, again, DITO generally performs better than deep matcher, but I think the key observation here is that DITO already performs better than deep matcher with half the amount of training data. So how do we see this? So for example, if you look at this row, with about 9,000 labeled data, DITO's F1 score is 84.36. And this is already larger than deep matches 79.94 for 25,000 label data. Okay, so that's the another consistent picture you get. We also conducted ablation studies here to determine the effectiveness of the 3 optimization methods. Summarization is always there because this is the hard limit of the pre-trained language models that we have to overcome. DA means data augmentation, DK means domain knowledge. I think the bottom line again is with all 3 optimizations put in is definitely better than no optimization, right? And some optimization put in is also usually better than no optimizations. Okay, so this last slide here, actually last experimental slide, I'm sorry, is the one with the internal company data set. Now these are huge data sets with 789K and 412K entries. So you can't simply do a Cartesian product and match all pairs. We actually have to implement blocking methods here, right? The first phase of before we can pass it to detour. So again, we have 96.5 F1 score there. Okay, so this is the complete end-to-end picture of the entity matching pipeline, including detour. Now detour is the box, the small box here, right? The end-to-end pipeline includes the blocking method, right? So to match company records, like I said, we have to implement the blocking method in real world because you cannot just do a Cartesian product. So in this pipeline, the first step is really to pass the data through the blocking function, for example, with keyword matching, just to find candidate pairs. And then second step is to sample some of the data coming out and label them so that you get training data for detour. Okay. And detour, remember, we have the 3 optimization method with domain knowledge, summarization, and augmentation, right? And finally, one thing that I didn't talk about, the data that came out from detour can also be used to build an advanced blocker, right? A blocker based on deep learning methods, right? For the next phase to determine whether 2 records match or not. So yeah, that's all I want to talk about for detour. In terms of related work, there's a huge list. I'm not going to go through everyone here, except to mention that there was concurrent work with detour at that time. The paper in EDBT 2020 by Brunner and Stockinger. They also applied pre-trained language models, but in that case without any optimizations, and obtained similar results that we have shown without optimizations. There are lots of entity matching based on recurrent neural networks, hierarchical-based deep learning solutions, and today ones that use transfer learning, active learning to alleviate the steep requirement of training data. Right? I'm not going to go through all this, but there are lots. Deep learning methods have also been used successfully in many other data integration tasks, like information extraction, whether it's about extracting named entities, relation extraction, opinion mining. They all reported very good results. Okay. Deep learning methods have also been successfully used in other data integration tasks like table understanding, curation, preparation, querying of tables and text. All right. So at this point, I want to take a step back and discuss why I believe deep learning models have been successful, right? And all these various data integration tasks. First, traditional ML machine learning techniques often require extensive feature engineering, right? Deep learning is especially good for tasks where rules are really difficult to specify and features are really hard to engineer, right? And many of these data integration problems are like that. So recall, for example, entity matching. The criteria you use for determining whether a pair of record match or not is different from another pair usually, right? And that's why a human reviewer is always so good, because they can apply different heuristics, different criteria to determine whether two records match or not, just depending on how the records look like. And that's what deep learning models are very good at. If you give it some guidance, they will adjust and try to understand what to focus on to determine match or no match decision. The other thing I think is that deep learning models are really good at dealing with dirty data, right? Data imperfections, when you have typos, you have missing data or values, they won't trip with all this dirty data. And that works because deep learning methods have a very deep, immense capability to learn from examples, right? It has been shown in literature that the lower layers of these pre-trained language models, such as BERT, right, capture more lexical meanings of the language, while the upper layers of BERT capture more semantic properties. And they are also able to track longer distance linguistic dependencies. And through all this is capable of distinguishing the difference between phrases that look highly similar and also phrased at the same time, right? Phrases that look very different but are similar, right? The example I give here is sharp TV versus sharp resolution, right? Some of the less deep models would think these two are matched, but we know as humans, like the word sharp here and the word sharp here, they mean totally different things. One is a brand name and the other is talking about the degree of the resolution, right? So, deep learning models can distinguish that. The other example I like is stop hair loss versus prevent hair thinning. These are completely different words out there, right? It would be a no match in most cases, but deep learning models, because they know the meaning of these words, they can tell you that these two phrases are the same thing. Okay, so so I will also add that it is this capability to learn from examples and pay attention to the right details is what makes it successful, right? As I mentioned earlier, for the second candidate pair, the addition number is important and somehow is able to figure that out, right? And for the third pair, is somehow able to figure that out, that the model number is important for making the decision of match here. Okay, so what's the catch? This all sounds too good to be true, right? So let's all use deep learning models from now on, right? Since they're so good. As many of you are probably aware, deep learning algorithms are very data hungry. The quality of a deep learning model is directly dependent on its training data. And actually, the more training data you throw at it, the better it tends to get, right? This is a slide from Andrew Ng's deep learning course. What it's saying is that, traditional machine learning model, which is the red line shown here, it plateaus with more training data. So you're not going to get more out of it even if you have 10 times more training data. But for deep learning models, these are small, medium, large neural network models. Especially for larger models, the more training data you throw at it, the better it tends to become. It seems to be limitless, okay? So the catch here is also, you don't just want to throw it training data, you want to throw it quality training data, right? So the higher the quality of the training data, the better it is, okay? So quality is very important here. So the quality of the training data is one thing. One also has to be concerned about other issues today, like fairness and biasness that may occur in the training data. So deep learning algorithm also requires usually high performance hardware, right? It's not easy to deploy. So it also has longer latency than traditional machine learning models. It's also more expensive to deploy in this case. It's also complex, okay? It has lots of hyperparameters. The largest GPT models these days, we're talking about billions of parameters. So just think it's really like a black box, why it's working or why it's not, right? And that goes to my last bullet here on opaqueness. It's not even, when you get an answer, it's not even clear why it's giving you that answer, right? Except that it's really good. some that's all, So going forward, I think there are lots of opportunities for the data management community. I believe we should put more effort to develop benchmarks for different data integration tasks. And these benchmarks should not just be about the data, but also include, or invent metrics to measure the fairness or biasness of data, right? In developing techniques for data augmentation, we should also pay attention to how data is augmented fairly. I don't think this topic is really paid attention to, except people just want to augment data and get more training data. There's also alternative methods to circumvent the data hunger issues that deep learning models face. These days, there are transfer learning, active learning, also weak supervision, and I'm starting to see more papers on these topics in the context of data integration recently. Okay. So another important thread of work is model explainability, which is the ability to explain your data integration results, right? So, so one idea is to use structure such as rules, which can be used to explain the black box deep learning models. Another thread of work is to directly explain the model's decision, like there's a line work that tries to find which parts of the input led to the prediction of the output. I believe there's a lot of room for more work in this area, and it's important to be able to explain your, in this case, matching decision, because sometimes these matching decisions are used for critical tasks, like if you want to, match jobs to, resumes, you better be able to explain why you're not matching certain cases, right? So this is very important. Yeah, what is the last point? Yeah, we should also understand more on how to answer queries on heterogeneous data. By this, I mean data not just with different structure, but also different modalities, like videos, images, which is occurring more and more these days. Okay. So just very quickly, last year in March, I think Andrew Ng also made the following two comments on an interview he gave, right? He encouraged people to take a more data-centric view of AI rather than a model-centric view, because there is a better chance of improving your model if you improve the quality of your data, right? The first quote says that when a system isn't performing well, many teams instinctually try to improve their code, right? But for many practical applications, it's actually more effective if you focus on improving the data, okay? And the second quote essentially is saying that all things being equal, the quality of the data is what differentiates your model from others, from another person's model, okay? So this is my last slide. I would like to end with this question, whether we can do data integration for social good. The world today, right, contains a lot of content online that are multimodal. Content can be a piece of text, an image, a video, or a combination of these modalities, right? So the world will be a much better place if we can better understand content that we share online or see online, right? And one question here is, can we integrate data well, broadly construed, to help better understand content? Can we find all duplicate content and understand which is the original one, right? Can we bring additional knowledge, external knowledge to a piece of content, and understand the relationship between different mentions of things in the content, right? Can we put all this information together to understand the true meaning or intent of a piece of content we see on the web today? So yeah, I want to, this work is definitely a result of good collaboration with Liang Li, Jinfeng Li, and Yoshi Suhara. They are no longer at Megagon Labs, but all different places now. And also An Haidon, who's still at University of Wisconsin. And also Alon, who gave comments to the slides, some of the slides. Yeah. That's all.
Okay. All right. Thank you. Thanks for the great talk. So I guess now let's open the floor for questions. If you have questions, you can, well, feel free to actually speak up, or you can also type into the chat box so I can read it. You can also use the raise hand feature.
Yeah. Okay. Thank you, Wang-Chiew. It's very nice to meet you here. Yeah.
Very nice to meet you. Oh my gosh.
Yes. We haven't talked to each other for many, many years. Yes.
Dr. Wang was my first advisor. Anyways, so I have. It's good to see you.
Yes.
Thank you.
Yes. I think the last time I see you is in Vancouver. You have I think 2008 in the Sycamore.
Yeah, one of the conference. Yeah.
Yes. Yeah. Anyway, very interesting talk. Although I'm not working in this area, I think I have learned quite a lot from you. Yeah.
Yeah. Thank you.
Yeah, but I do have one question here. I was just wonder whether this language model work well if you don't have texture data, mainly, for example, just structure column. Yeah, and have you studied the effectiveness, for example, removing the text part and only leaving the structure part, and what's the difference? Basically, I want to know how critical this approach rely on the availability of text data.
Yeah, my gut instinct is it's okay. It's doing as well because the experiments that we have. So like this structured, all these are just structured data without much text. DBLP, Walmart, they are not text. The ones with lots of textual data are textual by textual company data. So so the company data we have is also internal data, is also not much text, right? So I said it would work well. Right?
But in this case, even the baseline does not have. So all the algorithms you compare do not have a textual data. So what I think the question is, if compare with and without textual data, so you remove the textual part and see how much performance degradation will happen. That's what I'm.
Yeah, we don't have an experiment where in a table we remove the column with lots of text. Yeah, so we only have experiments where we have tables with not much text. Yeah, so
I see.
Yeah,
I see.
So,
and another way to look at this is probably if you don't have textual data, maybe I'll just do a simple neural network without language, without pre-train, and see in that case, how they compare. Maybe your training data is good enough. Training data for fine tuning is good enough to actually accomplish the matching task, right?
Yeah, I believe so. So this diagram is actually very important. I think if you're, if in certain cases like here, you're not going to get too much difference between deep learning models and traditional language models, right? If you don't have a lot of data, training data to begin with. I think the difference only comes in when you have a lot of training data, you start to see the gaps between all these algorithms. So chances are, if you don't have a lot of training data, you can just go for traditional machine learning models to run your algorithms. You're not going to see too much difference, right? Whether you apply deep learning methods or traditional ML methods. Yeah. So if you have a lot of training data, so yeah.
Yeah, it makes sense. Right. Thank you. Right.
Yeah.
Okay.
It's good to see you.
Yeah, good to see you. Very nice talk. Yeah.
Yeah.
Okay, great. So I think Tony has a question. Please go ahead.
Hello. Thank you for the talk. My question is on the domain knowledge injection portion. In the example, you added the ID tag to a word that was a model number. And I was wondering if you needed to do that for manually and for all the cases that you could find, or could you do it for like a small portion as a way to like bootstrap the algorithm so it can infer like the ID from other words?
Yeah, so we just did it on the fly before passing it into the model. You regex it, inject the token, and just pass it in. So we didn't do it like just for the training data and then not do it for the rest, if that answers your question. Yeah. Because it's
Okay, so it was like for every instance that you could find.
Yeah, because there's no reason not to, right? So
okay,
yeah.
Thank you.
Okay. Do we have more questions from the audience?
Yeah, may I ask one question? First of all, thank you very much for the very exciting talk. Yeah, I learned a lot from that. And well, maybe I look at the problem from a different angle. Let's say, well, nowadays we know when we feed more data and then we use deep model to get more potential, more gains from that. So one question to distinguish the database or the traditional data community with the machine learning very hot community maybe is that what would be the framework, no matter, what would be the principles to organize the data so that we can improve the deep learning models? Do you have any comments or advice on this part of the research? Because many people just say we play different tricks and those tricks just work. And the deep model they give us good results.
Yeah, so a lot of, I don't know, I read from a lot of time, even when we're doing this entity matching, a lot of the time is spent on preparing the data.
Yes.
Right. I think a lot of people in machine learning community have already been doing that without realizing that maybe we in the database community have been doing that perhaps even longer. Right. So they spend a lot of time prepping the data, cleaning the data, getting it ready, right, to pass to the model for training, right? So the part, at least right before training the machine learning model, I feel like, yeah, definitely we have a lot to offer here as a data management person, right? So, yeah, I think I also made a comment that, yeah, here actually, the quality of training data is expensive to obtain, and this is often a significant data integration problem itself, right? So this is the part where I think we can really come in and help. And the fact that to take a more data-centric view for machine learning as well is where we can come in and even collaborate on this space for that.
Because if you think about the old days, the grand success of database community is that when we talk about data quality, we have those normal forms. And then once you have the normal forms, then no matter what would the downstream applications, you will benefit from that, and we can measure the benefit. And when you talk about the when we talk about the efficiency, we have the indexing methods, we have the database systems, so that no matter the downstream task, we can provide the gain, and also we can measure the gain. And at this time, it seems to me for the deep learning things, well, we know we can offer something, but when people ask us exactly what you can offer, well, we can code and we can provide you the data.
I think the dirty part of the tedious part of the data preparation is definitely the part that is relevant to us, right? But I don't want to limit ourselves in this way. These days, I think we can also contribute on the machine learning side and the whole end-to-end pipeline on how to scale this. All right, scaling is something that I think we can offer a lot of help. Scaling and efficiency, right? So, which we know very well how to do all this. Yeah.
Yeah. Great. Thank you.
Yeah.
Yeah, just to add on the now versus then with traditional data model, I think now if you have this data lake thing, which I guess it further adds more complexity because you can dump all kinds of data in different formats and so on to it, and then it seems it's just at odds with us providing quality data. That's a kind of open problem maybe.
Yeah, so yeah, definitely data lake, and a lot of data is gonna be not in text, right? So this is the real thing. So I think the ability to work with all these different modalities is very important, right?
Okay.
That's
Do we have final questions maybe from the audience last round? Okay, so if not, well, thank you again, Wang-Chiew, for the wonderful talk, and it's really great to have you here virtually. So we're going to continue this seminar series in the fall and in the spring together with Professors Jianpei and Jianan Wang. So please stay tuned, and if you sign up for the like opt-in, checkbox for future talks, then we will also send an email to you for future talks. Okay, so let's thank our speaker again, and then that's about it. Hope to see you next time.
Thank you very
so
much. Thank you for the very nice talk. Okay, see you.
Good to see you. Yeah, thank you.
Yeah, bye-bye.
Bye.